In this lesson, we're going to talk about quantiles on the normal distribution. We're going to use the inverse normal distribution on the calculator. Now, I'll talk about what quantiles are after I've done this first example. So in this example, a population of crabs has a shell length of x millimeters. X is now the random variable, where x is normally distributed with mu equals 70 and sigma equals 10. Find the shell length of a crab that is longer than 95% of the crabs in the population. So this is a particularly long crab. 95% of the crabs are shorter than this crab. So first thing I want to say is, what is the distribution we're working with? Well, x, because it even gave us a name, is normally distributed with a mu of 70 and a sigma of 10. Now, we are told that the particular crab shell that we're looking at is longer than 95% of the crabs in the population. What we can say then is that the probability that whatever value we're looking for, x, is less than something. I don't know what that something is, so I'm going to call it k. That's the length of this particular crab. That probability is 0.95. Again, we are saying that we have a crab whose length we don't know. That's k. And if you look at the population, the probability that another crab selected would be shorter than our crab is 0.95. In other words, 95% of all other crabs are shorter than our crab. So the probability that picking a random crab, not ours, a random crab has a length less than ours is 0.95. The thing I don't know is what is k. So we're given a probability calculation or a probability value, the 95% or the 0.95, but we don't know what the boundary is on that probability. So that's what the inverse normal is going to help us find. So we hit second distribution on our calculator, and it again brings up this screen. Under distributions, of course, there's normal PDF, which we never ever use. There's normal CDF, which we've been using a lot. And then there's inverse normal, which is what we want today. So we scroll down to inverse normal, and then we hit enter. So we get a screen that looks something like this. It's called the inverse normal. It has prompts for area, mu, and sigma. Now mu is the mean, which is 70. Sigma is the standard deviation, which is 10. Area is the probability value, 0.95. That is what we call area. So 0.95 is going to go in for area. So in the area spot, we hit 0.95 and then enter. And now we want mu, which we said was 70, so we hit 70 and then enter. And then it wants sigma, and we said sigma was 10, so we type 10 and then enter. And so now paste is highlighted, so we hit enter one more time. So now our screen changes to say this: inverse normal, 0.95, which was the probability we knew, or the area, the 95%, comma mu, which is 70, comma sigma, which is 10. Again, if you're using the old operating system, once you do the second distribution inverse norm, it'll give you this prompt, and you have to put the 0.95, the area or the percent probability value, comma, and then mu, or the standard deviation, or the mean, and then comma, and then 10, or sigma, which is standard deviation. And finally, we'd hit enter one more time. So the calculator spits out this value, 86.4485, etc., etc. Now, this value that it just spit out is the value of k that we were not sure what it was. So I can now round this to approximately 86.4. So what we are saying is that if we have a crab whose length is 86.4, if the shell length is 86.4, then the probability that another crab that we select from the population has a length shorter than that 86.4 is 0.95. Or in other words, this crab is longer than 95% of the other crabs in the population. So that's what this has found. So this is an inverse normal because you have the probability value already, but you don't know what the value is that's in the inequality that you're trying to find. So now let's address the idea of a quantile. This 86.4, or this value of k, is the quantile that we were trying to find. In this case, it's the 95th percentile that we were looking for. So 95% of crabs are shorter than this particular crab of 86.4 millimeters length. I should probably add the millimeters in there. So quantile here could be percentile, it could be quartile, it could be any kind of what fraction of the way along the distribution have you gone. Generally speaking, when we say quantile, what we really mean is percentile, because that's typically the way it's going to be reported. But that's not always the case. It could be quartiles or whatever other kind of split you want. So it's a value that in this case is 95% of the way along that distribution. In other words, it is 95%, it's taller than 95% or longer than 95% of the other crabs in the population. This is very common with things like the SATs, where you get a percentile score. Whatever you have out of 800, that has a percentile score. And so if you had a percentile score you were aiming for, you could then look up in reverse what raw score you would need on the SAT in order to achieve that, and that would be that score that would be reported as, in this case, it's the length of a crab, but it would be reported on a 200 to 800 scale. All right, here's another one. The scores of on the recent math exam were normally distributed with an average of 84% and a standard deviation of 7%. If 32% of students scored higher than me on the exam, what was my score? And I want to round that to the nearest integer percent score. So first of all, x is distributed as a normal distribution with mu equals 84%, or just 84, and sigma equals 7%, or just 7. And I know that 32% of students scored higher than me. So I know that the probability that x, which is the whole population, the students in general, scored higher than, I don't know what my score is, so let's just call it k. That percent, or that probability, is 0.32. So this is saying, again, the entire population of students, of that population, those that scored higher than my score, whatever that might be, there were exactly 32%, or 0.32 was the probability of randomly picking somebody else who scored better than I did. Now, the inverse normal cannot handle this. It cannot handle a greater than statement. It can only handle accumulating until a particular spot, just like binomial CDF had to start at 0 going up to a certain value. Inverse normal has to start at negative infinity and come up to a particular value. So I need to change the way that statement is written. I need to write that as a probability that x is less than or equal to k equals, well, if 32% were bigger than my k, then 68%, which is 0.68, and I did that by doing 1 minus 0.32, or 100% minus 32%, so 68%, will have a score lower than my score, whatever my score might be. So I've written the distribution, I've written the statement that literally as given to me, what if 32% scored higher than me, 32% was the probability of a person randomly selected scoring higher than me. I don't know what my score is going to be, so I call it k. Then that would be the probability statement, but I have to change it to an inequality where x is less than or equal to k for the inverse normal calculation to work. So again, we do second distribution, we scroll down to inverse normal, and we hit enter. So the screen changes to the inverse normal screen. It's prompting us for area, mu, and sigma. It probably has old values in there, which I'm now going to change. So again, the area has to be on an x less than or equal to k. It has to be accumulating from the left to a k. So I don't want to use the 0.32. That is not going to give me my answer. I want to use the 0.68, which is the area to the left of my k value. So the area value is going to be 0.68. And now it prompts us for the mean, which of course was 84. We hit 84, enter. And then it wants the standard deviation, which was 7. We hit 7 and enter. And finally, once paste is highlighted, we hit enter again. So the screen will now say inverse norm, 0.68 for the area or the probability value, 84 for mu, and 7 for sigma. And we are now going to hit enter one last time. So now the calculator spits out this value. So this value is the unknown k that I didn't know from my probability statement. So I can write that value down. K is equal to 87.2738961. Now the question was, what was my score round to the nearest integer as a percentage score? So obviously this was already as a percentage because 84% I just wrote 84, 7% I just wrote 7. The 32% of students, that was a probability statement, so that was 0.32. And then I changed it to a 0.68 to do the complement of that. And then I got a k value of 87.27. So this is my quantile, my 68th percentile value. So my score was 87%, again, nearest integer as a percentage score. So again, what happened here was we had a mu, we had a sigma, and we had a probability statement saying that 32% of students scored higher than me. And so I wrote that statement as probability that x is greater than k, that's my score, is equal to 0.32. X is all students, k is me specifically, but the probability that a student randomly selected is going to be having a higher score than me is 0.32, but the calculator can't handle inverse normal in this direction. It can only have x less than or x less than or equal to as a probability statement. So I changed that. If 32% had scores better than me and 68% had scored worse than me, or I suppose equal to me, technically speaking. Although that's not going to matter for normal distribution calculations. So then I go to the standard, the inverse normal, and I do second distribution. I found inverse normal. I put in the area, which is the probability 0.68, mu is 84, sigma is 7, and I got my k value, or my quantile value, and then rounded it to the nearest integer as instructed, so I scored 87%. Just a quick comment I want to make on this problem. So if I had accidentally forgotten this rule about the statement has to be an x less than or x less than or equal to statement, and I'd use 0.32 for the area instead of 0.68. So I thought this was the correct statement, and I did inverse normal that way, I would have gotten a score of 80.7, so 81 essentially. But if you look at the problem, you would have known immediately that can't be right, because only 32% of students have scored higher than me, which means I have done better than average, because the average on a normal distribution should be at the 50th percentile. 50% of students will do better than average, 50% of students will do worse than average. So if my score is about an 81, that's below average. So that means that more than 50% should be better than me instead of less than 50%. So I would know something went wrong here because my score should be better than the average because only 32% of students scored higher than me. So I would know something is wrong, and hopefully I would then realize that I've done something wrong. I've forgotten to rewrite this as a less than or equal to, x less than or equal to statement in order to do the problem. Okay, a couple more quick ones. Find k such that the probability of x greater than or equal to k is equal to 0.8 when x is distributed as a normal distribution with mu equals 25 and sigma equals 4. I don't have to rewrite that. It's already given to me. I just need to work this out. The problem with that one, though, is that it's an x greater than or equal to k, which the inverse normal cannot do. So I'm going to change that probability, the probability that x is less than k, is, well, if the probability of x greater than or equal to k is 0.8, then the probability of x less than k is 0.2 because it's 1 minus 0.8. So this is actually the statement that is meaningful for my inverse normal. So on my calculator, go to second distribution, go down to inverse normal. Area is going to be 0.2 because that's the way that this statement is written. Mu is going to be 25 and sigma is going to equal 4. And so inverse normal 0.2, 25, 4. I hit enter and I get my answer, which I can now round to the required 3 sig figs. K is approximately 21.6 because it was 21.6335, etc., etc., etc. Now here's another one. Find h such that probability that z is less than h is equal to 0.25. Well, z is a special normal distribution. Z is the normal distribution where mu equals 0 and sigma equals 1. So that's the distribution I'm going to use on my calculator in the inverse normal. Now this is written as z less than h. So it's written in the correct inequality where the z is going to be less than whatever number I'm trying to find. So we're accumulating up until whatever number that is, and the area or the probability is 0.25. So now we're ready to go. So on my calculator, under the inverse normal distribution, I make area equals 0.25, mu equals 0, sigma equals 1. And now when I round my value h to the appropriate 3 sig figs, I get negative 0.674 because it was negative 0.67448, da 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 da. So this is now the required 3 sig figs value for h. And that is the end of the lesson.